Welcome back to my whiteboard. I'm Kevin Dorma. This is part 4 of the control series, and we will look at level control. Let's consider the example of a reflux drum for a distillation tower. We maintain the level in the vessel by modulating the valve that sends the product to a downstream process. The vessel was designed to provide 2 minutes of hold-up time from normal to the upper alarm point. We should keep in mind that the objective for level control is not really to maintain the level on set point. Instead, the objective is to provide a smooth flow to the next process, while keeping the level between the allowable limits. A smoothly changing flow is always better than sudden changes to the flow rate. We need to understand how level control behaves in order to determine a good way to tune a PID controller. Let's consider a step test on the level by closing the control valve 1%. This causes the level to ramp upwards. In our case, we will consider a time delay of 10 seconds. The important thing to note is that this is not a stable or self-regulating process, like temperature from a heat exchanger. In this case, the level will rise indefinitely. This is a non-self-regulating process. This often causes problems where people are used to working with self-regulating processes. We define the process gain as the change in slope that is produced by increasing the valve position by 1%. The original open-loop Ziegler Nichols methods were not designed to work with level control. Fortunately, alternative methods have been devised for Ziegler Nichols. Lambda tuning for level control uses different recipes for the PID constants. A principal feature of lambda tuning for level control is that we can target the response time to fit inside the available hold-up time. We will pick a response time of 2 minutes. Let's see how these two tuning methods manage a change in level set point and a load disturbance. First, I had to scale the PID output by a factor of 20 to get the output to fit on the same scale as the level. Let's run the modified Ziegler Nichols tuning. The set point change is managed very quickly and displays some oscillation. There should be no real need to change the level set point quickly. A set point ramp should be used instead. The real test is how it manages the disturbance. The disturbance is caught in 40 seconds and the level is brought back to set point within 100 seconds. The controller does not utilize very much of the available hold-up time in the vessel. The fast response comes with oscillations in both the controller output and the flow rate to the downstream process. Now for the lambda tuning, where we target a 120-second response time for the level controller. The set point change is not quite as bad, but we still need to use a set point ramp. For the load disturbance, the rising level is caught in the specified time of 120 seconds, and the level is gradually brought back to set point over 600 seconds. The controller is utilizing the available hold-up time in the vessel, and there are no oscillations in the controller output. To wrap up, Ziegler Nichols tuning produces oscillations in the flow rate to the downstream process. Lambda tuning is designed to utilize the available hold-up time and produces a smooth change in flow rate without oscillation. I prefer lambda tuning methods for level control because it allows me to utilize the hold-up time that the designers have provided. Next is Part 5, Pressure Control. I'm Kevin Dorma. please visit my website at www.kevindorma.ca. Take care.